Greetings everyone, welcome to the first part of lecture 30 in our multivariate calculus class, Math 353. So last lecture we burned through the material that we needed from chapter 13 and we are now jumping into chapter 16, the final chapter of the book and the last topic that we will consider in this course, that being vector calculus. So vector calculus, defined broadly, is the study of two main concepts, that of vector fields and line integrals. And we are going to start today by thinking about vector fields. We're going to talk about them, define them, sketch some examples, and then we will begin thinking about a special class of vector fields known as the conservative vector fields that we will study in greater detail in part 2 of this lecture. Again, you'll notice that the date is 4/22, and I am posting this on the evening of 4/23. We are on track to get caught up with the lectures and getting everything posted. I do anticipate posting tomorrow, the 24th of April's lecture, on the 24th of April, in fact. I'm going to get it up on Friday. I do not know that I'll get it up before our regular meeting time, as I had agreed to do initially, but I'll try to. And I will hopefully be able to stick to that schedule moving forward for the remainder of our lectures, the last 2 weeks that we have of class. So, define a vector field. A vector field on Rn is a function from Rn to Rn. Our main concern in this class is with 2 space and 3 space, so we'll be thinking about vectors on the plane and vectors on R3. Vectors on R2, vector fields rather, on R2 take this form. So big F, we generally use a capital letter to designate vector fields, and they also get the vector hat notation as well because they do output vectors. So big F hat of x and y is going to be a vector, the first component of which is a scalar valued function of 2 real variables, and the second function is likewise a scalar valued function of 2 real variables. So here little f is mapping R2 to R and little g is mapping R2 to R. These little f and little g here are just like the types of functions that we learned to take the partial derivatives of, and they are also the exact type of function that we learned to integrate over regions of the plane. Now we're sticking 2 of them together and making a vector out of those 2 functions. So we're creating a vector that has such a function as each of its components. On R3, somewhat predictably, big F hat of x, y, z is going to be 3 scalar valued functions of 3 real variables. So here for R2, I can feed big F hat any point in the plane, and it's going to feed that xy pair into little f and get a number back, and into little g and get a number back, and so it's going to return a vector. You give it a point as input, this is the input space, 2-dimensional in this case, and it returns a vector of the same dimensionality as the point that was input initially. So you feed this big F a point in the plane and it spits out a 2-dimensional vector. You feed this big F a point in 3 space and it spits out a 3-dimensional vector. A vector field on R2 assigns every point in the plane a 2-dimensional vector. So every point in the plane could serve as input to such a vector field, and it assigns to that point, or it associates with that point, a 2-dimensional vector, the output vector that corresponds to that point as input. And we can draw these output vectors with their tail sitting at the point where that was the input value that gave rise to them. So if I pick any point in the plane here, and we will do some examples, I could plug this point in the plane into my vector field. It would give me back a vector as output, and then I draw that vector here with its tail anchored at its associated input point, the point that gave rise to it. And you end up getting pictures of this sort for 2-dimensional vectors. So we're seeing arrows, vectors for this point, points in that direction. If I take this point and plug it into my vector field, I'm getting a vector that points to the right here. I just made up a picture here. Generally, we will have formulas that give us our vector fields, but I'm just trying to illustrate what the sketch of a vector field looks like generally. And a way that I like to think of these as I like to think of vector fields in many different contexts as some kind of a current map. So every point in space has a motion vector associated with it that could be the current that one would experience if they were to place themselves in that point in space. So for a two-dimensional vector field, you can think of it as a very shallow river, and we see the water flowing to the right over here. It's moving sort of northeasterly over here. Something's happening over here. So maybe this is water that's getting poured on top of a little hill, and so it's flowing off in different directions. Or you can also imagine, take a tabletop or a desktop, put very small walls all around the sides of that tabletop so that you could put a small layer of water on top of the table and it would be held there. And so you imagine having this very flat, very thin layer of water on top of a planar surface, and you might see that water moving in different directions at different points. And a two-dimensional vector field could represent that kind of information. So each arrow here, we have different arrows at different points, and each arrow gives you some sense of what the current or what the movement is at that point. For three-dimensional vector fields, a three-dimensional vector field assigns a three-dimensional vector to every point in 3 space. And so these are also like current maps, but they're more like thinking about the flow lines in a wind tunnel or due to the actual wind outside, for instance. So every point in 3 space, just take the room that you're sitting in. Presumably you're listening to this lecture inside. If not, that's fine. Think about the space that you're in outside. Every point around you is a point in 3 space. At each point, even if the air is very still in your environment, it's likely that there's some movement of the air at every point around you. And you could imagine assigning a three-dimensional vector to each point in 3 space that points in the direction in which the air is moving. And in fact, the length of that vector could also represent the velocity with which the air is moving at that point. So we have both direction, or rather I should say the speed, velocity being direction and speed. But we will assign to every point in 3 space in our immediate environment a three-dimensional vector that represents the velocity of movement of air at that point. And that gives us a three-dimensional vector field. Your book has some lovely pictures, much nicer than I can draw. I definitely encourage you to have a look at pages 1108 through 1111 of your book. These are the opening pages of chapter 16 and our discussion of vector fields. And please do have a look at that. It is definitely worthwhile. You can also Google examples of three-dimensional vector fields, and you'll see lots of nice images. They are beyond my capacity to draw, so I'm not going to attempt to, but I do encourage you, in fact, implore or harangue you to please have a look at images of that type. It is helpful to develop some intuition for the types of objects we're discussing at this point. That being said, we are going to focus on two-dimensional vector fields on R2, because I can draw those in a more reasonable way. And most of what we do is going to correspond in a lovely way from 2 dimensions to 3 dimensions in a fairly straightforward way. So we're going to focus on two-dimensional vector fields because they're easier to draw, easier to represent, but also because our ultimate goal is to discuss a pair of important theorems in vector calculus that apply to two-dimensional vector fields. So we're going to cap off this course with a discussion of Green's theorem, and Green's theorem applies to two-dimensional vector fields. There are analogs to Green's theorem for three-dimensional vector fields, but that is not in the curriculum, though it is covered right at the end of Stewart's book. So if you're interested in that, I encourage you to have a look. It's also a topic that is covered in Calculus 4, if you have a chance to take that course here at SUNY New Paltz. So let's try some examples here. Let's let big F hat of xy be the vector given by just xy. Sketch this vector field. So when I go to sketch this vector field, first thing I'm going to do here, which you don't necessarily have to do each time, is identify what my little f function is and what my little g function is. So here, little f of xy is x, little g of xy is just y. So these are particularly simple functions of 2 variables. And what we're going to do to try to sketch this function is pick some input points, plug the input point into our vector field equation, find the vector which is the output associated with that given input point, and then let's sketch that vector with its tail resting at the input point that gave rise to it. So for instance, I could pick point 1, 0. This is an obvious point to pick. We like to often think about this point. I'm going to plug 1, 0 into my function for my vector field and see that big F of 1, 0 is just the vector 1, 0. So I come here to the input point 1, 0, and I sketch the output vector, which also happens to be 1, 0, with its tail resting at that point. Likewise, I might pick a point 1, negative 2 here in the plane, plug that into my equation for the vector field to get back 1, negative 2 as the vector, and so I sketch the vector 1, negative 2 with its tail resting at point 1, negative 2. This vector field, don't read too much into the fact that we're having the input point be exactly the same as the vector which is output. That's a particular characteristic of this vector field, so that doesn't always happen. This one is actually known as a radial vector field. All the vectors point along radii out from the origin here, so it always moves directly away from the origin along radial lines, and it's going to play a particularly important role when we come to think about the concepts of divergence and curl within a few lectures here, sometime next week likely. So this is my sketch of this vector field. Let's have you try one of these. So let's let big F hat of xy be the vector negative y comma x. I want you to sketch for me this vector field. So grab some points, some random points. You might pick 1, 1, 1, negative 1, negative 1, 1. Consider several fairly obvious points relatively close to the origin. Plug those points into your vector field, see what vector is output at that input point, and then sketch the output vector with its tail resting at the input point. Go ahead and pause the video and give that some thought. Alright, so let's have a look at it. So if I plug in 1, 0, I get back vector 0, 1. Just looking at my formula, the first component is the y component. The first component of my output vector is the y component of the input point, which was 0. Or actually it's negative y, which negative 0 is 0. And the second component of my output vector is the x component of the input point, which is 1 here. So I come over here to point 1, 0, and I sketch the vector 0, 1 with its tail resting at 1, 0. And likewise, I can pick lots of other points, and I can plug them into my vector field, and I can find the output vector, and I can sketch it. So here at point 0, 1, we're sketching vector negative 1, 0. And then I have to put in some of these little diagonal points on the edges here so that we don't end up drawing a swastika, because nobody enjoys that. But this is ultimately what the vector field comes to look like. If you sketch lots of different points, you'll see a vector field of this sort, which we would call a rotational vector field. This is one that we're going to learn to call a rotational vector field. So it always sort of spins. It never moves directly away from the origin. Instead, it always spins in a counterclockwise direction around the origin in some sense. So this rotational vector field, and backing up a bit, this radial vector field are both going to be important examples as we begin to consider divergence and curl. This one is sort of all divergence and no curl, we'll learn to say, and this one is all curl and no divergence, to begin to use those words and hopefully develop some intuition for what they mean. Alright, let's have you do another one of these. So let's let big F hat be the vector field given by x comma negative y. Sketch big F hat for me. And that should be sufficient time for you to have paused the video. So let's have a look at it. This one turns out to look something like this. So we have points from above moving down towards the x-axis and then sort of along it in either direction, breaking either right or left as we move from above and down. And likewise, points below the x-axis are going to move up towards it and break right or left depending on their orientation. Whereas the y-axis just pulls straight in towards the origin and the x-axis straight away towards the origin. And I've sketched a few points here, a few that I've actually computed, but you would generally want to look at more than 3. So I don't mean to indicate that this would be sufficient for me to have drawn this picture, but rather this is the idea of the kind of calculations that you perform in order to draw the picture, and ultimately you can begin to see the pattern and maybe sketch in a few extra curves that weren't explicitly computed. So another example of a vector field in R2. We have actually already encountered an entire class of vector fields. So just as when we started talking about vector-valued functions, I said that we had already met one. It was the parameterization of the line. Now we're talking about vector fields, and in fact we've already met a class of these as well. Gradients of scalar-valued functions are vector functions, vector fields, I mean to say. So any gradient that you compute when we were discussing partial derivatives, all of those gradients were vector fields. When we drew gradients, we said that they, at every point in the plane, so if you have a real valued function of two real variables, that's one of our landscapes that we like to talk about so much. Every point, the xy plane serves as sea level, and then we have a series of peaks and valleys all above sea level where there is a height assigned at each point in the xy plane. And the gradient of such a scalar valued function was a vector field that assigned a vector to every point in the plane, which pointed in the direction of maximal rate of change for that function at that point. So it was a function that assigned a vector to every point in 2 space. So as an example, to remind ourselves of how gradients work, if I let little f be x squared y, that is a real valued function of 2 real variables, then the gradient is going to be a vector made up of the partial with respect to x as the first component and the partial with respect to y as the second component. And this is the vector field that I obtain as the gradient of little f. Likewise, if I drat, so this should be a function of x, y, z. That's a typo there, my apologies. But if little f is a function of x, y, z given by x cubed y squared z, then the gradient of little f is going to take this form. Here's my partial of little f with respect to x, with respect to y, and with respect to z. And that is a vector field on R3. It assigns a 3-dimensional vector to every point in 3 space. Whenever a vector field, so we're going to learn that not all vector fields are the gradient of some function. When you have a scalar valued function and you take its gradient, you do generate vector fields. And there's a whole class of vector fields which are the gradient of something. And we are going to call those vector fields conservative vector fields. Not every vector field is arrived at by taking a gradient of some function. So there are vector fields which are not the gradient of any function. But those vector fields which are a gradient, for which there does exist some little f, such that the gradient of little f gives you that vector field, those are special. Those are important, and we are going to study them in greater detail. They are known as conservative vector fields, and the little f, whose gradient gave you big F, that little f is called a potential function for big F. So we're going to define those formally now, conservative vector fields and potential functions. If you have some big F mapping Rn to Rn, so it is a vector field on Rn, we call it conservative if there exists a scalar valued function of Rn such that the gradient of little f equals big F. So you already have a vector field, big F, in hand. If it turns out to be the gradient of some scalar valued function of n real variables, then we call it a conservative vector field. And in that case, we call little f a potential function for big F. So conservative vector field and potential function, when we say conservative, we don't mean conservative in the sense that they're voting Republican. We mean conservative in the sense of conservation of energy. So it is a conservative vector field in the sense of conservation of energy, conservation of momentum, these kinds of physical ideas. And it's a potential function in the sense of potential energy. And these vector fields, these types of vector fields, are going to be a key mathematical tool in modeling the types of physical phenomena that have these types of conservation laws and this concept of potential energy associated with them. So things like conservation of energy when it comes to something like the change of potential energy due to your position in a gravitational field, for instance. So, or the change in position in a region where there are perhaps some static electrical charges distributed throughout the region. So there's different levels of electrical potential in different regions. And that potential function, or that the level of potential energy at each point could be a potential function, and the electrical field generated by that electrical potential is going to be given by a conservative vector field in that kind of context. We are going to talk a bit more about these ideas and how they relate to physics as we talk about the fundamental theorem of line integrals. So in another lecture or two, We'll be discussing the fundamental theorem of line integrals, and we'll be better equipped to have a discussion about how the idea of a conservative vector field relates to conservation of energy, and how the idea of a potential function relates to potential energy. But it is true. I mean, you can imagine if you've got our landscape and for a real valued function of two real variables, the peaks and the valleys represent something like potential energy, and the gradient always points uphill, so in directions of higher energy. If you actually were to consider it as a physical landscape, and you were to allow a marble to start rolling around on that physical landscape, the marble would always move exactly opposite the gradient, barring considerations of momentum, I suppose. But generally, water, as we talked about when we talked about gradients, water always moves opposite the gradient because it's always moving directly downhill. That's why it always crosses the level curves of a topographic map in a perpendicular manner. So all of these ideas are going to be connected. This is some of the mathematics that's used to model the kinds of physical phenomenon where you have conservation laws and the concept of some kind of potential energy. So some vector fields are conservative vector fields. They arose as the gradient of something. Other vector fields are not conservative vector fields. There is no potential function whose gradient will give you such vector fields. How do you tell the difference? How do you know if a given vector field is a conservative vector field or not? And the answer is given by this theorem, identifying conservative vector fields. So if f hat is a vector field and its two component functions are little f and little g, and little f and little g are C1, meaning all of their first order partials are continuous. So this is some notation we defined previously in the course. If I say something is C1, I mean that its first derivatives are continuous. And here each of these is going to have two first order partials. So all four of those functions have to be continuous. The partial of f with respect to x, with respect to y, the partial of g with respect to x, and with respect to y. All four of those functions are continuous. Then your vector field is conservative if and only if these two partials are equal. So I'm taking here the partial of g with respect to x, and I require that to be equal to the partial of f with respect to y if I am to consider, or if I am to be able to conclude that this is a conservative vector field. So it's relatively simple to check whether or not a vector field is conservative. It just involves taking two first order partials, which is not a difficult thing for us to do at this point. It is worth noting that we are taking the partial of the second component function, g, with respect to the first variable. Backing up a page really quickly, g is the second component function in the y position in some sense, and we're taking its partial with respect to x, and likewise we're taking the partial of the first component function with respect to the second variable here. And that is no mistake. So if everything is nice enough so that both of your component functions are C1, so continuous first partials everywhere, then your vector field is conservative if and only if this equality holds. So for example, here's a vector field. This is not one that I made you draw out because it's considerably more complicated. It would be difficult to draw, though it could be done. All you have to do is plug in xy pairs and follow through, compute the vector, and plot them. But we are not concerned with drawing this vector field at the moment. We just want to know whether or not it is conservative. So is this a conservative vector field? So this first component is my little f here. My first component function, little f of xy, is going to be 4xy plus y cosine xy. I'm going to take the partial of that with respect to y, the second variable. So the partial of little f with respect to y, and this is the expression that I get. There's a product rule involved, and one of the derivatives in that product rule also involves a chain rule. And ultimately, this is the expression I get for the partial of f with respect to y. Little g is my other component function, so here it is, 2x squared plus x cosine xy. Here's my little g. I take its partial with respect to x. So this is the partial of the second component function with respect to the first variable. And taking that partial with respect to x, again, there's a simple polynomial, easy enough. There's a product rule involved in differentiating this with respect to x. And in taking the derivative of the cosine function with respect to x, there's a chain rule that occurs with another extra copy of y popping out, with an extra copy of y arising due to the chain rule here. And these are the same. So the partial of f with respect to y turns out to be the same as the partial of g with respect to x. Since those are equal, I know f hat is conservative. It is a conservative vector field. The next obvious question would be, okay, well, can we find the potential function, or a potential function, whose gradient is big F hat? And we are going to do that. We are going to learn to find big F hat's potential function. In fact, we should be able to do that in part 2 of today's lecture. And you'll also note that I marked out something here. I started to say little f. It's pretty traditional to use little f to refer to the potential function. For this problem, I'm using little f also to refer to the first component function. So you can't do both at the same time, right? If you're going to use little f to refer to the potential function whose gradient is big F, then you can't use the same symbol to refer to that first component function at the same time. So just be aware that I am using little f to mean different things in different contexts here, but that should be okay. We get to use the same symbols over, or else we'd run out of symbols pretty quickly. So we are ultimately, we at this point can determine that this is a conservative vector field. Shortly we will be equipped to find the potential function whose gradient is big F hat. So let's have you do one of these. Here's big F hat. It is a vector field, a slightly simpler one here. Is it conservative? So go ahead and pause the video. This isn't terribly difficult, but go ahead and pause the video and decide whether or not you believe this is a conservative vector field. Alright, so let's have a look. If I take the first component function and take its partial with respect to y, I'm going to get x plus 1. I then take my second component function and take its partial with respect to x, and I get just 2. These are not equal, so the partial of the first component function with respect to the second variable is not the same as the partial of the second component function with respect to the first variable. Therefore, big F hat is not conservative. So, no, big F hat is not conservative. That is to say, there does not exist any little f such that the gradient of little f equals big F. It is impossible to find a scalar valued function whose gradient gives you this big F. So there are lots of kinds of vector fields. There is a smaller or relatively small group within the space of all vector fields that are called conservative vector fields, and those are going to be of particular interest to us. We'll wrap this part of the lecture up now, and in the second part we will learn to find the potential function associated with a conservative vector field. Thank you, folks.